Hello, my name is Andres Morales, and in my project titled COVID Behavior in a Racially and Politically Diverse State, we will be looking into the COVID-19 pandemic for the state of Texas. Just a little bit of introduction and the research questions. So the background: state of Texas is one of the worst responding states in the COVID-19 pandemic, record-setting amount of cases per day on multiple occasions, and it was common to see a multitude of social distancing violations. The state government action was abysmal, as there was no statewide mask mandate until July 2nd. As a result of that, many communities, primarily minority communities such as Southern Dallas and San Antonio and El Paso, were very heavily hit by the COVID-19 pandemic. In addition, politics influenced how people responded to the pandemic. Historically, Republican voting counties such as Briscoe and Motley have some of the highest 7-day average cases per 100,000 people out of the state, while Travis County, which voted 71% to then President Biden in the 2020 election, has one of the lowest 7-day average cases per 100,000 people. So my research question in summary is out to seek how each of the 256 counties have fared with COVID to date, and more specifically, are there any explanatory variables relating to race or politics that could help explain the case for population of each county? I have 3 general research questions I will be analyzing throughout this presentation pertaining to a combination of these 6 explanatory variables. One is the percentage of the county population limited English speaking ability, the percentage below the poverty line, the percentage that lack a high school diploma, the percentage that attend a 2-year college minimum, the average high school graduation rate of the high schools in the county, and my categorical variable is a political party receiving the majority of the vote in the 2020 election. Here are my research questions. Question 1, do characteristics commonly associated with Texan Hispanics, so lack of English speaking ability and living below the poverty line, has a significant linear impact on the case for population ratio? Question 2 is analyzing whether lacking a basic high school diploma will have a larger or smaller linear effect on the case for population ratio than living below the poverty line. And then question 3, does the voting result from the county in the 2020 election influence the case for population of the county, regardless of their high school or college education, with the statistical hypotheses listed below? My data acquisition, so my data came from 3 major sources. The data for the case for population came from the Texas Department of State Health Services. You can see the link there below. The quantitative data came through a Kaggle database containing social health data from all U.S. counties. And therefore the Texas county were just extracted from that database. Link is below. And then the categorical data for the 2020 election result was obtained just from a CNN election results page with the link below. We now dive into trying to statistically prove or disprove research question 1. Do characteristics commonly associated with Texan Hispanics, which are lack of English speaking ability and living below the poverty line, have a significant linear impact on the case per population ratio of each county? Before that, let's introduce our data set characteristics. We have our variable names right there and definitions of each, the units of each, the quantitative, if they're quantitative or qualitative, and then their range. The sample size would be 254, which matches the amount of counties that there are in the state of Texas. And before mentioned, we talked about where the data was coming from. The Y data was extracted from the Texas DSHS case documentation. The X data was extracted from the Kaggle database. All data was combined into one CSV file for our analyzation. Our preliminary analysis showed our initial regression equation y equals negative 11.55 plus 6.93 x1 relating to bad English, and x2 relating to below the poverty line, and has a coefficient of 0.1259. The plot showing variables plotted against each other showed 2 major problems, mainly the multicollinearity between poverty and English, and 2 potentially influential cases, cases 162 and 155. The original plot showed non-constant variance. As you increase x, the variance gets more negative, and then Shapiro plot highlights potential normal distribution violation. Our model building and diagnosis, so let's check these influential cases. We use student-deleted residuals because we identified those to be Y outliers, and we will compare the SDR values of those cases to a t-critical value of 3.7749. And if that SDR is greater than the t, we will reject the null hypothesis, and the case is not an outlier with respect to Y. McLennan County, which is case 162, had a very high SDR score, and therefore we will conclude that it is a Y outlier. In the same story for Maverick County. I made the executive decision to remove those data points from analysis, which we talk about later in the presentation. Checking the clean data for violations, which are new regression equation, violations still show, the Shapiro plot still showed normal distribution violations, and the residual plot, although it improved, it still showed a lack of consistency. Therefore, I concluded that we should transform the Y data into using a box-Cox transformation, and that resulted in a lambda value of 0.108. Our final model report and applications, we have our transformed cleaned regression equation as seen there. Our R squared improved from 0.06741 to 0.07403, which is not a great increase. Therefore, we know that these explanatory variables do not explain a lot in the change in Y. However, our root mean square error improved from 132.9 to 8.896. Therefore, we can conclude that they're removing the outliers as well, in addition to transforming the Y data through a box-Cox transformation helped out with reducing the error. However, to make further conclusions on why we must back transform the data. ANOVA sum of squares was used to evaluate the research question, whether beta 1, which is the bad English, or beta 2, which is below the poverty line, equal to 0. You can see that both p-values were less than any alpha value that could be commonly used, and therefore we conclude that the explanatory variables have a significant, albeit small, linear impact on the case for population ratio for each county in the state of Texas. With an increase in 1% of each explanatory variable, the case population will rise. This might be due to Hispanics not understanding safety guidelines, government officials not taking the pandemic serious enough, and that Hispanic populations tend to be at a higher risk for COVID-19 due to health conditions such as high blood pressure and diabetes. We will now dive into statistically proving or disproving research question 2. Does lacking a basic high school education have a larger or smaller linear effect on the case for population ratio of the county than living below the poverty line, or are they relatively the same? Let's introduce our data set characteristics. Ratio and below poverty stay the same, but now instead of the lacking of English ability, we will now introduce high school, which is the percentage of county population that lacks a high school diploma, with the units, type, and range there. We identified 2 outliers in research question 1, and therefore to maintain consistency into research question 2 and 3, we will eliminate those from the data set, and therefore sample size decreases to 252. Preliminary analysis shows massive multicollinearity problems between poverty and high school, which logically makes sense, as if you lack a high school education, you're more likely to live below the poverty line. Superior plot also shows potential non-normal distribution violations. However, it is hard to make violation conclusions when there is excessive multicollinearity. Therefore, the remedial action that I decided to do was to focus on the multicollinearity first and assess the violations after. Our modelability and diagnosis, we first use the best algorithm to try to find the best model. We can use this best algorithm to see one of the explanatory variables suggested to be dropped by R to reduce multicollinearity. However, unfortunately for us, finding the best using this algorithm did not solve the multicollinearity issue, as it selected the model with both predictors, as it included the smallest SSE, largest R squared, smallest CP, and smallest price. Another tool we have disposable to us is ridge regression, which used to penalize point estimates by a subjective value lambda. There are different ways you can select this lambda. If you use a generalized cross-validation, R will output a lambda value of 82, which doesn't really make any sense. However, if you use a ridge regression to reduce MSE or reduce the VIF to around 1, it outputted a lambda value of 0.1. Applying that lambda value to 0.1, we generate that ridge regression equation that you can see in front of you. The R squared did not improve by much. The residual population superior test still concludes that violations and regression existed. And off screen, I did a quick box-Cox transformation, and it yielded the same results. The data still did not follow normal distribution, and the variances were non-constant. Therefore, due to the remedial measures not fixing the multicollinearity issues, the research question cannot be accurately answered. I did a simple SLR model of each individual predictor, and it yielded similar point estimates with very small and very insignificant R squared values. As you can see right there of 0.0412 and 0.044. The conclusions that we can make is that neither explanatory variable, even with the remedial measures, does a good job in explaining the response. The SLR model shows that the variables are too similar and that there's no benefit on combining them because they explain these same changes in Y. And they're too insignificant to make the research questions conclusions. The next step that we can take is to revisit the data collection for explanatory variables, trying to identify sampling biases and abnormalities. If we can potentially identify those, then we can revisit the research question, run the models again, apply ridge regression, apply the best models, see if their results have changed, and potentially we could better answer or give an answer to the research question too. We will now dive into our third research question. Does the voting result for the county influence the case for population of the county, regardless of the high school and college education makeup of the county population? To introduce our data set characteristics, we maintain the same response variable ratio and now introduce three new explanatory variables: college, high school, vote. College is a percentage of the county population that has attended a 2-year college minimum. High school, which is different from the high school variable introduced in research question 2. This now represents the average high school graduation rate of the high schools in the county. And then vote, which is our categorical variable, which is representing the political party receiving the majority of the vote in the county during the 2020 election. The categorical variable will either have a 1 or 0 value for X6, with 1 being a Democratic vote and 0 being a Republican vote. As we talked about in research question 2, sample size is now 252 due to the 2 outliers that we took out. Preliminary analysis of the model shows the initial regression equation shown there with an R-squared value of 0.08. There seems to be no multicollinearity issues between the college and high school. However, the superior graph does show potential normal distribution violations, and therefore our remedial action that was selected was to select the best model to check whether high school or college can be eliminated from the model and see if that can affect the Shapiro plot, as the residual plot shows no real violation. Model building and diagnosis. We fit the best model with a stepwise algorithm, which is a measure used to determine if one of the explanatory variables can be dropped. If R can suggest to drop one of the explanatory variables, R suggested to drop the high school variable as it reduced the AIC. Now we have our new regression that only depends on college and the vote, with an R-squared value of 0.1575, vastly improving the R-squared, but slightly with a root MSE of 8.864, slightly reducing, leading to a slight increase in the root MSE. To validate this, we use a K-cross validation, which reduces similarity between training sets and the use to validate regression models. We get a similar root MSE of 8.5569. Therefore, the K-fold validates the stepwise algorithm model. Now we look at established model violations. Residuals still seem to be good. However, that the normal distribution is still violated, but like we talked about in research question 2, that has to do with more of the potential sampling biases and abnormalities in sampling rather than the actual model. And therefore, in the future, we will go and revisit that sampling procedure to see if there's any biases or abnormalities. We will also check for interaction between college and vote with a null hypothesis and alternative hypothesis stated right there. We perform a GLT test and concluded that there is no interaction between college and vote. Our final model regression equation is shown there. As we talked about, our R-squared improved drastically and our root MSE slightly worsened, with the K-fold validation confirming the correct model with similar root MSE. To answer our research question, we will use a GLT test to determine whether beta 6 is equal or not equal to 0. Running that test in R yielded a statistic of 17.194 and a p-value of less than 0.001. And we reject the null hypothesis that beta 6 is equal to 0 and conclude that the case for population for each county in the state of Texas are not the same when analyzing 2020 election results. That means that the Democratic counties and Republican counties had different case per population, significantly different case per population ratios. Counties that voted Republican had a higher case per population than counties that voted Democratic, and there's a multitude of reasons for that. The rhetoric from Austin or Washington, or the potentially Republicans being less willing to sacrifice their liberties. As we would talk about the outlier analysis for why we took out those 2 outliers, Maverick County and McLennan County. Maverick County, the 57th county in population, but had the 3rd highest average case, 7-day average case per 100,000 people. McLennan County, 21st in county population, but the 2nd highest between November and January for the 7-day cases per 100,000 people. This is the basis for why I determined to take out those cases as either such abnormal data points that it contributed to influencing the model in ways that we did not want to. Here are our references for anyone who was curious. I hope you guys enjoyed my presentation and you guys have a great rest of your day.